Thank you, Janos, for that kind introduction. I'm really happy to be here today. So, today I'll be talking about architecting for power efficiency in general purpose computing. And yesterday, in Amir's keynote, he talked about 2 to 3% of the world's energy consumption is going to computing. He neglected to say that this is projected to grow to 10% by the end of the decade. So we, and I mean all of the people in this room, all people who contribute to computing, we have a responsibility to make sure that energy is used efficiently. General purpose computing. General purpose computing remains extremely important, and we must continue to advance this. And if you look at the, recent years' product announcements, it's clear there is still a lot more to go for general purpose computing. But, when I look at the program at Micro and ISCA for the last few years, you would think there was nothing left to do, right? So, this is also a call to arms. I mean, what happened to general purpose computing research? It's in a really sad state, and there are lots of areas that need work. So, bring on your wild and crazy ideas. This is just a few things that I just, thought I'd just throw out there. Take a couple of these ideas, combine it with whatever you're working on today, and approach these problems from a new perspective, and let's, reinvigorate the world of computer architecture for general purpose computing. So what am I going to talk about today? I'll just very briefly talk about my background, and then I'll go into the meat of the talk. And the meat of the talk is essentially 3 aspects: thermal density, what can we do from a microarchitecture and design perspective, what are some of the strategies for that, power efficient core strategies, power efficient multiprocessor strategies. So Janos mentioned a little bit about my background. I first spent like 20 years in Intel products doing a bunch of, first started with GPUs and then decided that, if I'm working at Intel, I should really do CPUs. So did a bunch of CPUs and then moved to Intel Labs, and then I have recently returned to the product team. So I'll just highlight a couple of projects. My first CPU was the 3D6SL, and it's not just the 3D6. So if you can see the bottom left, that is the 3D6SX. It had 275,000 transistors, and 3D6SL was really Intel's first SoC, and it was targeted for laptops, mobile computing. And you can see that the 3D6SX is only in terms of area, a small fraction of that 3D6SL die. The rest of it was all brand new. And for the 3D6SX, we had a team there that was converting this to CMOS technology. The blue part is what me and my team worked on. Essentially back then, the people talked about set associative caches. There were a lot of papers about that. And it was viewed that 8-way set associative caches are just really expensive, and when would we ever build something that big and complex? And it just seemed a little bit out there. But we put that in. It was this on-chip cache controller supported up to 128K, 8-way set associative, and the actual SRAMs were off-chip, but the controller and the tag RAM here is on-chip. Also on the right side is all the control for the 3D6, 87, SX, and things like that. Another kind of trivia thing to note is that back then we could put our initials on our chips. So I actually have my initials right in that spot right there, and it's a little blurry, so, you know, it's a D with a horse head and an M, and, you know, it was always a little fun to put your initials on. Some learnings, you know, back then we didn't have like detailed performance simulator models with traces and all that. We did all the modeling using, you know, analytical models and things like that. And, you know, the 386 SL was surprising in the large performance leap and as well as the power efficiency that it achieved. And mainly it was because, you know, having that on-chip cache controller as well as the on-chip memory controller reduced the latencies and actually had an outsized performance impact. And, you know, it was higher than what we had anticipated. Integration is a good thing. I also worked on the Pentium Pro. I was, you know, the multiprocessor architect, and, you know, back then this was pretty famous. It, you know, there were a lot of myths back then. Oh, x86 cannot be fast. x86 is only for home computers. You know, workstations, servers, high-performance computing, you know, it will never fly. I think we broke those myths, and, you know, the Pentium Pro was also our first multi-chip package. Inside the package we had the CPU chip, and then next to that, if you look in the package, there's the L2 cache, which was configurable to 56K, 512K, and 1 meg. And as you can see on the right side, you know, Intel took market share. What happened to all those RISC CPUs, right? Okay. Then this is the, you know, what we called at the time network microarchitecture. I was a hyper-threading architect for this, and, you know, that was a really fun project. Again, CPU from scratch, and I was also the multiprocessor architect for this. And in 2001, we introduced the Intel Xeon MP processor on the left, as well as, you know, we introduced the hyper-threading on the Pentium 4, and, you know, again, pretty fun project. Then Haswell, I was the chief architect, and we launched Haswell in 2013. It was, we called it, the brand name is Intel 4th Generation Core. And for this one, it was kind of a return to my roots kind of project because it was mobile focused. And my first CPU project was mobile focused. And so it was really fun to, you know, come back and do power, battery life, performance. We put in a whole bunch of features working with Microsoft to enable something called Microsoft Connected Standby. I, you know, wanted to do something for responsiveness, better, faster, and more efficient, right? So we launched this, and we launched essentially 15 watt and 6 watt SoCs, and there's a die floater right there. 1.4 billion transistors. And then that was the last CPU I did for the product side before I transitioned to Intel Labs. Intel Labs, I started a new lab. We called it the Accelerator Architecture Lab, and we had a really awesome team. We have actually 2 people in the audience here from that team, Erico and Asit, so you can talk to them if you would like this. And, you know, the team's expertise. We had really strong CPU, GPU, FPGA, accelerators, and compiler expertise. And we very quickly decided that we were going to focus on machine learning and deep learning, and, you know, we were going to deliver ideas for the next 10 to 100x performance. Our focus really was, you know, we did a lot of work on, so at the time we anticipated, we said, okay, machine learning, all this AI stuff, this is really going to take a huge amount of compute. And one of the things we said is that, this is going to enable, your grandmother to program her computer, right? So, lots of things are just going to change dramatically, the amount of compute needed, and, these matrix multiplications, which are order n cubed, this is just not going to be sustainable. Sparsity has to be part of the solution. So we did a lot of work on sparse algorithms back then, and we also investigated, reduced precision computation, and reducing precision involves a lot of risk. There's accuracy, there is convergence issues, so you cannot just use it indiscriminately. But you can also, there's also the potential, machine learning, it's all about, balancing overfitting with generality, and you're just constantly balancing those. So, can we use sparse and reduce precision to help with that generality? And we did find that we could use it sometimes to improve accuracy. So then I have recently transitioned back to the products team, and unfortunately I can't talk about what I'm doing today. So you guys are just going to have to, make do with, I'm going to talk about concepts and strategies, and, I think we as a community, we, have to realize computers make the world go around these days, right? You've got a computer in your pocket, you've got a computer in your desk, you've got a computer in your car. You cannot buy anything without interacting with a computer. Computers are everywhere in our environment. Today, computers are what makes the world go around, right? We make computers, so we make the world go round. Well, and the other thing is Moore's law is not dead. There's just amazing innovations. Breakthroughs continue at a rapid pace. If you look at this graph, which is completely public, just from 2010 until now, we are adding zeros. We've added almost 2 zeros since 2010, right? And, if you talk to process technology folks, these transistors that people are talking about, amazing. There's new materials. There's wiring and connections. How are we wiring all this stuff together? There's 3D stacking, growing transistors, layers of transistors, and stacking die, right? Packaging, thermals, power delivery, architectures. It is not stopping. So, and then I just put this graph together, actually just 2 days ago. But, if you look at the silicon area is not adding as many zeros. So silicon area is still growing, and multi-chip modules are enabling us to continue to, develop more silicon to satisfy the computing demands of the world, right? Early multi-chip modules were, IBM had the Power 1 and Power 2, which were 9-chip and 8-chip modules, respectively. Intel, our Pentium Pro that I talked about earlier, that was our first 2-chip module. And today, multi-chip modules are state-of-the-art. And this is allowing us to pack even more compute together. And, packing things together is a key to power efficiency. So this is part of the story. Although, if you look at the client SoCs, the client SoCs actually stays pretty flat, between 100 and 200 millimeters squared. And, so power density is really a problem as we pack all those transistors in. And in fact, as I was putting together some graphs for power density, actually someone pointed out to me Fred Pollock's Micro 32 Keynote in 1999, where he showed this slide. I mean, from the 386 to the 486, all the way to the Pentium 3. On the x-axis is Intel's process technology nodes. On the y-axis is power density. And he put some interesting things onto this. The hot plate, the nuclear reactor, rocket nozzles, right? This is a pretty fantastic slide. So I have to include this, right? How do I not include this? So I plotted the same 7 points that Fred Pollock had on his slide, and instead I used, for the x-axis, year. Right? So much easier for me to plot the years. And you can, and then I added the, or one of my guys added the rest of the high-end desktop parts to this. And so you can actually see that the power density is continuing to increase. And if you look at, I try to use the same type of scale here. If you look at this nuclear reactor thing, we have exceeded that. Actually, I guess you can't see my pointer down there, but we have exceeded that. So, right, and you know, there actually has been discussion about the accuracy of Fred Pollock's slide, and there's people have said, oh, that nuclear reactor thing is off by 3x. But you know, this is a log scale on the y-axis. The 3x, it's still, you know, in that range. So regardless of that, we actually are cooling. And also, you know, on this power density thing, these are our desktop products where we're like, and we're running at maximum voltage. So this would be the hottest power that we can do. But how are we able to achieve all this? It is thanks to, you know, our incredible thermal management colleagues who do research and engineering in this area. So huge credit goes to them for figuring out how to manage the thermal solutions. In the past, we had heat sinks and fans. Today, we have new materials. We have liquid cooling. We have these really cool liquid gas phase-changing solutions delivered in the form of heat pipes or vapor chambers. In the future, there's all kinds of people, you know, talking about embedded cooling. So as we have these, you know, 3D stacked, you know, configurations, how do you, you know, get cooling in there and embedded in there? There's also new materials, so lots of exciting things. I really hope that they can continue to figure this out. But we must also address this problem. And we, as a microarchitecture community, we need to have solutions. So, microarchitecture and design, we have a responsibility to mitigate thermal density while meeting high-performance computing needs. So, with great power comes great responsibility, right? We've got great power, we have a responsibility, right? So, now I'll just get into the meat of the talk here. Part 1, thermal density. How can we address it using microarchitecture and design? Part 2, power efficient performance. How do we achieve that? Core strategies. And then followed by part 3, multiprocessor strategies. And, oh, by the way, lots of people keep asking if I'm going to reveal any secrets. All the graphs that I'm going to show are not going to show our actual future-looking products or process technologies. I have created these in a way so if you go and measure this and to try to like figure out what we're doing, you will be misled, so don't even try. Okay? All right. Thermal density. But the concepts are accurate, okay? The concepts are very, very relevant. Okay, thermal density strategies. What can we do from an architecture and microarchitecture and design, right? So thermal density, let's just start with the equation. Thermal density equals to power divided by area. If you can reduce the power, it directly translates to improvement. If you grow the area, that also improves it. And let's talk about microarchitecture design solutions. So let's start with actually this graph. This is a performance versus power graph. Performance on the y-axis, power on the x-axis. And this graph is defined by the equations on the top left. Performance equals IPC times frequency. IPC, I think everybody in this room knows, but just in case, instructions per cycle. So it's the average number of instructions that a microarchitecture will execute, right? And if you have a wider, deeper, more execution ports, better branch prediction, et cetera, your microarchitecture will, on average, execute higher numbers of instructions per cycle times frequency. Frequency is how fast are those cycles going. Power is equal to leakage. There's the static component, which is the leakage power. Then there's a dynamic part C V squared F. Capacitance. You gotta drive all this capacitance. Then the voltage to drive that overcome that capacitance, and then frequency. So, whenever you look at these types of graphs, the first thing you need to do is your eyes need to go and find this point, okay? So, first thing, it's a very important point. It's essentially the point where to the left of it, it's linear, to the right of this is this V squared F component, right? So, what is this point? It is our power at minimum voltage. Transistors cannot operate below some minimum voltage. They just don't work. So, and so below this point, essentially this equation, V becomes a constant. And so C V squared F is a constant. And everybody took linear algebra. Maybe we all forgot, but you all are math people. So this becomes a linear function with respect to frequency. And so that is why this region to the left of the power, this point, is referred to as the frequency scaling region. And you generally want to stay out of that unless you really want to reduce power, but you're going to pay a pretty steep cost in performance. To the right of this is where we are, so the other point is Vmax, and that's the power at Vmax. And so in this region is where we are doing voltage scaling. As you increase the voltage, the transistors can operate faster, and so your frequency can go up. And generally, between Vmin and Vmax, this is a 10x power range, and there's a 2.5x performance range. So obviously, I put the equation for thermal density on the top right, power divided by area, and we can see that if you are running into thermal density issues, you can turn down your voltage, and this can pretty much give you a direct correlation to thermal density improvement. So thermal density, as you need to, we can adjust that knob, and it's a very important knob. And if you look at this graph, it is steeper on the left part of that curved area, and so if you want to operate at a more efficient point, you may want to operate further to the left. If you really need performance, you can operate further to the right. Okay, another important aspect is hotspots, because hotspots can actually be our limiter before the overall thermal density that you average over a larger area. And hotspots move around a lot depending on what you're doing. So if you're doing some very memory, cache-intensive of operations, you'll see actually the region near the cache light up and be turned, these are images of a die using infrared emissions imaging. And so you can see that. If you have pretty intense integer operations, some of the areas near the out of order logic will light up. And if you're doing some FMA stuff, it'll light up over there. So what can we do to address hotspots? Today, essentially what we do is we spread it out and control those hotspots. So if you and we do a lot of pre-silicon work as well too, and as well as post-silicon imaging to see where we affected. Pre-silicon we do simulations to see where the hotspots might be, and we can break up and spread out those hotspots. And silicon is an excellent conductor. So if we strategically place cooler structures near those hotspots, it can very quickly dissipate these hotspots. And so you want to actually strategically place those structures. Another thing is if those techniques don't work, then we may, and we do, duplicate some logic, and then we can shift and rotate the work to different areas, right? And so that allows the logic to cool down. Also, a very important aspect is sensor placement. These thermal sensors they're not cheap, I would say. And so you need to place them strategically, and those sensors allow us to have some dynamic thermal control. So, you can insert some delay to slow it down or make other adjustments in order to control your hotspots. So these are some things that we do. And so in summary, this is the end of the first section here. Process technology just by the way it's shrinking the area pretty dramatically, generation over generation. It just makes the thermal density problem a lot worse. And we do various things, voltage, breaking up and controlling hotspots. And that last bullet there is area is your friend, right? The denominator is area, so if you grow area, the overall thermal density improves. Do we want to add dark silicon? No. So find something useful to do with it, right? Maybe when we want to grow buffer size so we can get more IPC, maybe want to grow some caches, right? These are fairly cool types of structures that we can do that improves performance. So the research challenge that I want to throw out to the community is, there are things that we are doing, but I think there's a lot more. So if you were to do a microarchitecture that directly addresses thermal density, what would you do? What kind of microarchitecture would you come up with to really, solve this problem in a different way, right? So that was part one. Let's move on to part two. So power efficient performance, core strategies. So let's first talk about the metrics. We no longer live in a world where power is we can just spend as much power as we want. We all live with a budget, and so the first metric would be, for a given power budget, how can we maximize performance? So maximizing performance for that power is making the most power efficient use of that power budget. Then the other one, the next metric is for a given SLA, like service level agreement, right? For a given performance requirement, can we deliver that performance at minimum power? So these are the two metrics for power efficiency, power efficient performance. And again, I'm going to bring up the same graph, note the point. The first question people always ask, well, what about process technology? how does process technology help? And process technology essentially moves the process, up and to the left. So diagonally up to the left. Up and to the left is the good direction, right? Higher performance, lower power. And process, there's actually there's hundreds of parameters that you can optimize. So any process technology may emphasize maybe some more shift further to the left, or more shift to up, right? Depending on how you choose all these different parameters and optimize it, you can shift it a little more, a little left. Now the metrics are up at the top right there: power budget, max performance, perf requirement, min power. So, I just put a line here so we can measure it, right? And near V min, next generation process, clearly we get, look at that vertical line and where it intersects the purple curve and the green curve. Clearly we can get, if it's this process technology, approximately 10 or 15% near the V min. Here, again, we get good performance, and here we get good performance. So we get better power efficient performance at a fixed power budget. What about for the performance requirement? Here, if you need this high level of performance where you were maxing out your voltage, you can actually, achieve that performance at in the mid-range of your voltage level. And because of that, power equals, the dynamic CV squared F. That V squared F part is pretty compelling. So you actually save quite a lot of power at this high performance level. Then in the medium area, right, you still save a good percentage, and then near V min we save some. So process technology, clearly a good winner. CPU microarchitecture, the topic of today's conference, right? How does CPU microarchitecture, the performance features that we know and love to add to our CPUs, how do those impact performance and power? And there is this misconception that, if you grow the area, you're gonna add capacitance, you're gonna add leakage, and it is not good, right? So let's examine that. And when I'm talking about CPU microarchitecture performance features, there's actually quite a range. There are performance features that don't cost very much area at all, very minimal. Then there are performance features where you need to add a new structure, right? So, but you take a bunch of these features, pack it together, put it out into a new microarchitecture, and generally it does grow the area. So it shifts the graph up and to the right, and it shifts it up and to the right because the IPC features generally need some area to implement. So that is the leakage component, and leakage will go up, and then it will also increase, the capacitance that we need of the die, right? So that is why the curve shifts up and to the right, and you can see this V min point moved up and to the right. So if we use our vertical lines to measure this, at V min we can near V min, it's a tiny little bit. It's not that compelling. At mid voltage range, it is a larger percentage, and then at near V max, this is you can get a pretty good performance boost from doing this. So this is power efficient, right? By definition, power efficient. What about the second metric? given a performance requirement, some level of performance, can we reduce the amount of power that we need to spend to deliver that performance? So here at at the high performance range, again, look, it is pretty compelling, right? We can actually say we can deliver that same level of performance, and again, it's because of this V squared F component, right? Mid-range performance, still gaining. Low performance, still a gain, right? So microarchitecture innovations do improve both efficiency, right, for both metrics. And there is a caveat. We're looking above Vmin, and I'll get to below Vmin in a minute. But this is why I would like to encourage the research community to come back and look at CPU microarchitecture performance for general purpose computing. This is the motivation. Now, let's take process and microarchitecture together, right? So, process technology shifts up and to the left, but we have thermal density problems, and we can do more without all those transistors. So, shift the graph up and to the right and repeat, right? So, process and microarchitecture work together to allow us to get better, more efficiency, moving forward. So there's a lot to be gained. And as you keep adding this, and if you were to draw the horizontal lines, you can see that, yes, this is actually pretty compelling. Okay, what about efficiency at lower power in this box, near Vmin and below Vmin? There's a lot of compelling reasons why we would want to do work here. Let's zoom in on this region. And again, process technology helps, moves up and to the left, even in this region. Still very, very helpful, right? If we were to use all those metrics, it's a very good thing. Microarchitecture performance features, as I mentioned before, moves up and to the left, and you can see as we zoom in, it actually moves the curve in this region, in the wrong direction. So it does not help. So what does help? So there's a lot of different libraries you can choose when you're doing a design, right? You can do, larger cell libraries, smaller cell libraries. There's lots of processes, technologies that you can choose. So if you were to choose, some small cell libraries, low leakage process, and then if you resynthesize things to lower frequency target, your synthesis tools will pick smaller transistors, which will shrink your area, which shrinks your capacitance, and you can move this curve down and to the left. And so low leakage process technology and lower frequency targets do help. But if you want to move it, that that Vmin power point even further to the left to get efficiency, if you're interested in the power efficiency further to the left, then you would come up with a solution that has a lower capacitance and lower leakage in order to achieve that point. And really, if the power range that you want to target is, some width, right? You want to make sure that that blue dot is placed to the left of your range in order to get the best usage of that. And this is the reason why, hybrid, everybody's doing hybrid these days. And this is the reason. So now you can do all your analysis. Essentially allows us to, get a larger power efficient scalability range. It extends the range both to the left and to the right. This is not I don't believe this is the only way to solve the problem. And I would like to challenge the research community to think about how can we solve this, in other ways as well, right? This is a key tool in the toolbox, but let's see, are there other ways? So, summary, power efficient performance, core strategies, process technology helps, but hurts thermal density. So opportunity, let's add performance. Adding performance features helps both thermal density as well as power efficient performance. And then, and then below the beam endpoint, so hybrid microarchitectures, key. Both of these, all the hybrid microarchitectures as well as all this stuff, it helps thermal density, so it solves both problems. But I believe that there is a lot more we can do. So if I throw out the challenge to the community, can you come up with new and different microarchitectures that meet high performance and thermal density in other ways, right? So throw out, come up with your wild and crazy ideas. I would love to see it. Okay, part 3 is multiprocessor strategies for power efficient performance. So before I get into that, I'd like just a little, let me just talk a little bit about Amdahl's law and MP scalability. And then we will use the same 2 metrics that we used in the last part 2 of this talk. For a given power budget, max performance, for a given performance requirement, minimum power. And and then let's just take a quick look at Amdahl's law before we get into that. So everybody here knows Amdahl's law, right? But here's just a quick reminder. Execution is equal to the serial part of your code plus the parallel part of your code. And the parallel part of your code, you can, spread it over some n numbers of cores, and everybody knows this. So, and so if the classic graph on the right, I just reproduced that. If the parallel portion is 90%, then you're limited by your serial part, and your max speedup is 10x speedup, etc. If it's 99%, your max speedup is 100x. So, is this very power efficient to run 8,000 cores to get 100x speedup? Maybe, anyway, I think it's not so power efficient. But, if you look at this equation and you're taking the parallel part and you're dividing by n, n means that your MP scalability factor is perfect. You're getting full utilization out of every core that you add. I mean, how often do you actually see that such perfect parallel kernel speedup? You don't, right? So, just measuring the super simple thing that everybody knows about spec CPU 2017, right? Spec int. And you just graph the components of the spec integer components from Leela, all these components, and you just graph it. This happens to be on Sapphire Rapids, from all the way up to 56 cores, and they compute the MP scalability for each of these components. You can see that for the bottom one, it is the MP scalability is 0.97, and for the one at the top, it's 0.99. For floating points rate, it ranges from this MP scalability of 0.9 to 0.98, right? So, and for these are workloads where there is no serial portion, right? We're just running n copies of the applications. No serial portion, no OS portion. OS is maybe 1% of the execution time. So all those OS issues, it's not even factoring in here. There's no logs, there's no communication, right? So, but, and then what are some of the factors that impact MP scalability, right? So on the software side, everybody in the room here is familiar with all these things, this long list of things that can impact how well you can scale. And then on the right, again, all the hardware people in this room, these are the problems that we keep working on, right? So all of these things impact our scalability. So let's now incorporate MP scalability into Amdahl's law. So Amdahl's law graph on the far left with parallel portion at 99% and perfect MP scalability. And so you can see that our performance asymptotically approaches 100 because of Amdahl's law. Now, how do we modify it? So here's the equation. Amdahl's law, execution time is equal to the serial part plus the parallel part. But now, instead of dividing by n, let's divide by this function, right? The MP scalability. And the resulting Amdahl's law scalability is right here. So, you thought Amdahl's law was bad. You factor in MP scalability, it gets worse, right? So you thought you could get to 100, you're actually getting to 50. Now in data centers, we can, the reason that MP scalability is hitting those things is because we're running into some kind of bottleneck, right? And let's say that in our data center, we've got super smart algorithms. You can, batch together with your AI algorithms, all kinds of jobs that each job is running into a different scalability problem. So in that earlier long list of things where none of them are hitting, any common scalability problem. So we've got a lot more scalability, a lot more parallel portion. And let's just say that the parallel portion is now 99.5%. And let's say the MP scalability is now 0.995. And so where does this go? It does improve the asymptotic thing, and it actually does push this graph out to the right, so more cores are possible. But it's still, pretty limiting. I originally had a lot more slides in here, but it was clearly this talk was getting way too long. So I just want to talk very briefly about CPU core utilization in clients. We have the ability to profile, lots of client systems. So this is like profiling system over, 458,000 client systems. And these are the 8-core systems, okay? And you can see that the percentage of time that any one core is active, there's a good percentage of time for that. And then any n cores are active, so max cores all active. And you can see that the biggest bumps are, any one core and any n cores, right? And on the right is a 4-core system. Again, 1 and n. You can see this when you go to 16 cores, regardless of the number of cores, it continues to follow this pattern. 1 core and n cores. And then in between you have this roll off, 2 cores, then 3 cores, and So, the priority is 1 active core, then n active cores, and when you're executing those n active cores, again, Amdahl's law and the MP scalability of the workload should be factored into the overall power budget and performance of the workload. So this is one observation. Now, I don't have the graph, so when in an infrastructure as a service, IaaS, right? When people go and buy an instance type of something, and they rent, say, 4 vCPU container or VM, right? 4, 8, or 16. It is also not uncommon, if you look at the core utilization within that container, to see this type of a shape of core utilization. So, 1 core and n cores, and then these containers. Now the unit of compute is how many of these types of containers can you simultaneously support on your MP multiprocessor system, and you can do the math and you calculate the scalability using these containers as your unit, and you can do Amdahl's law and MP scalability and all the stuff that we know and love, right? So I'm running out of time, and I still want to allow a couple of questions, so I'm just going to finish up really quickly here. Multiprocessor efficiency, single core performance still matters. If from each core we can get more performance at that power budget, that improves the efficiency, less power at that performance target as well. And Amdahl's law and MP scalability still factor in. So those are pretty important reasons why single core performance still matters, even in a multiprocessor world. Concluding slide for section 3, power efficient performance. Amdahl's law, MP scalability limit our ability to scale up. The data center folks are doing everything they can to overcome some of those limits, but we still need to factor that in. Power efficient performance from each core matters, and I'd like to throw it out to the research community again. Now, add in these multiprocessor nodes for data center scalability. How do you co-optimize that and cores for high performance and thermal density? There is a lot that can be done. There's a lot of further power efficiency that we can squeeze out of the system. And I'm not even talking about all the software. There's a tremendous amount of wastage in the whole software stack, and I'll leave that for the software people to optimize. But you guys, anybody in software, you're wasting a lot of power out there. Okay, so I'm just going to throw this slide up as my concluding slide, right? Again, we need more research for general purpose computing. Bring us your wild and crazy ideas, and leverage all the other things that you have learned in these years that you've been doing GPUs and machine learning, and apply it to general purpose computing research. And that's the end of the talk.
Thank you, Debbie. Thank you for sharing with us your journey and also setting the path for the future. We already have time for a few questions. Yeah, please go ahead.
Hi, this is Mahesh from Ampere Computing. Thanks for this talk. I wanted to ask you about the power performance curve, the orange one, where you're showing microprocessor features make the curve go up. When it goes up, that's kind of like the final result. That's what we're trying to go for. Can you speak about how you get there and the choices that you make to move that curve up, and the process that you use to get to that point?
The process that we use to come up with microarchitecture features, like essentially it's a lot of the stuff on this page, right? We have performance simulators that we measure, that we model the features, and we are always collecting new traces of different workloads, and of course we can only collect traces for today's workloads, and what about tomorrow's workloads? So we also come up with ways to model tomorrow's workloads, and essentially we do a lot of detailed simulations to estimate how the performance can improve, and then we actually use a lot of the techniques that I discussed today to figure out, does that power efficient or not? Next question.
This is Jenny. Future Week.
Okay.
Sorry. Okay. All right. Thank you. A quick question on the core active power per day chart. From any 1 to any all, sounds like if you add them up, it doesn't add up to like 100%. Is there like a zero active power?
Yes.
Okay.
So the most, I did not plot zero because the most common is zero. And if I plot zero, you can't see like the 2 core active, 3 core active, etc. So yeah, this is when any core is active, how many cores would be active. And the biggest, for clients, the biggest percentage is actually the 0 core active.
So this is still in the data center, or
No, not in the data center. In the data center, that is not the case.
Hi.
So the reason I brought that up is because the relative percentages of, so you would probably renormalize those bars for the data center.
Then Young Jimenez, Texas A&M University. Thanks for a great talk. I love this slide. I love that the first word is branch prediction. I love working on branch prediction and memory hierarchy and much of the stuff on the slide. It's really hard, and it's hard to get students interested these days because of all the other things that are interesting to them. It's really hard to get funding. Really super hard to get funding. So Intel has been pretty good about sending money to folks like me. Not enough. I mean, I can fund maybe one student on what NSF. We sent a proposal to NSF on this stuff, and they came back and the reviewer said, "We want you to work on accelerators instead." They kind of basically said that. So, what can you say to people who want funding and or are in charge of funding and are maybe afraid to work on hard topics to encourage us to do this kind of work?
So I think all of us should be lobbying NSF. So yes, Intel, we do fund research for general purpose computing, but we need everybody else to step up as well. So all you people who work at all these other companies, help fund the whole research community. Like, don't be stingy, right? And yes, I think the NSF and other places, we do need to increase the funding. I fully acknowledge that. The funding for this needs to improve, and I would like all of you to use your connections to encourage, we will continue to fund research and encourage everybody else to also contribute to the pot. This is very important. I totally agree.
Thank you.
Next question.
Hi, Xin Lam from Tsinghua University. Thank you for your talk. If chiplet is involved, I assume that it can solve part of the thermal problem. Will oil's assumptions change? And what's your comments about the train of chiplet? Thank you.
Wait. Can you, so chiplet?
Assume that we have our big SoC, so we're going to cut it into 3 or 4 pieces. The thermal, as far as I am understanding it correctly, the thermal is not the whole power. It's about hotspot, right?
Yeah.
If I can break it into many pieces, so the hotspot will release or disappear or something like that. Am I correct?
I'm having a little trouble understanding. Maybe we can talk about this afterwards. Okay. So, next question.
Hi, Amir from Google. Great talk. So I think it may sound like a cliche question, but we see a lot of increase in the machine learning applications, and machine learning application requires a lot of general purpose computation as well, for data processing, other kind of computation. Do you think how machine learning application changes the conventional wisdom of how we build CPU and how it changes like how we should structure all these ideas.
Okay, I think the question is about how does machine learning algorithms and the computing required for machine algorithms change all these ideas. So,
I'm talking about the accelerator part, just more
accelerator performance. Okay,
yes.
so actually my talk was originally about CPUs, GPUs, accelerators, and FPGAs, and I decided that to change the topic of my talk a few days ago to general purpose computing research because we need more ideas. But in the end, all of the things that I just spoke about apply to accelerators and all of that, right? Thermal hotspots. When you talk about the performance per accelerator, it actually has that same graph, applies to accelerators. And then as you're scaling those things out, all of the Amdahl's law and MP scalability still applies. So in fact, this also applies to all the accelerators work. Next question.
Last question.
Bon Metz from the University of Toronto. Thanks for the really interesting talk. I have two questions, but they're really short, so I'm going to pretend it's one. So one is you showed the thermal hotspots. Can you give some sense of the magnitude? So that, you obviously showed they're hotter or cooler. How different is it in degrees Celsius between the hottest and coolest parts of the die?
I don't know.
Thanks. And then the second question, I think you kind of answered this, but just to confirm, the data on core usage was from a client computer, but in the data center you say it's similar, just the 0 bar wouldn't really be there, but the other distribution is pretty similar in the data center?
Yes.
Okay. Thank you.
Yes. There's a lot of different workloads, and there's also a lot of different variations, right? So even in the client, right, when I showed this graph, right, if you look at games, the distribution is quite different. Maybe I should have showed a bunch of different graphs, but like different workloads actually have a different distribution. This is sort of a average across a whole bunch of things. And it would be the same in the data center. Like your particular workload is going to have a different distribution than someone else's workload. But if you take a whole bunch of people's workloads together and average them out together, you would tend to see this type of distribution. But your usage varies depending on the specific workload.
Thanks.
Okay. Last question? One more? Okay.
Last one. I'll keep it simple. So Boris Grant, University of Edinburgh. Nice talk. Thank you. For people who want to do the CPU research that you're encouraging, what workloads should they be looking at? A simple version of the question is, does spec still matter?
Does spec still matter? You are speaking to my heart, actually. Yeah. So if you look at workloads are changing a lot. The way people are developing applications is changing a lot. And yes, I don't think I have time to go into all of this, so maybe we can talk afterwards. But yes, we should be looking at future workloads. And in fact, one of the emphasis that I do is we look at the application developer trends, and we essentially try to, follow that out to how people are running the new application behaviors and the number of threads, all kinds of the jitters, all of these types of things. So yes, we should be looking at how applications are being developed in the modern time and in the future, and targeting our hardware designs to those future workload behaviors.
Let's thank Debbie once more. Thank you.